Welcome back to Code Meets World, and today we're going to be looking at our first problem in the math and geometry category, which is called happy number. I'm excited for this math section because I've always really loved the programming crossed with math problems. I think they're really fun. So here we're told that we need to create an algorithm to determine if a number is happy. And a happy number is defined by the following process. If we have a positive integer, replace the number by the sum of squares of its digits. Repeat this process until it goes to 1, or it loops endlessly in a cycle which does not include 1. Those that end in 1 are happy. Return true if it's happy, false otherwise. And I see we have two examples here. I'm just going to go straight to the whiteboard because I think the best way to talk about this is by doing it ourselves and seeing what we get. So let's go through this for n equals 19 and see if we get the same answer that they got. So we'll set n as 19. So it says starting with any positive integer, replace it with the sum of squares of its digits. So that just means we do 1 squared plus 9 squared. Square each digit, add them together. That gives us 1 plus 81, which would be 82. Now we do the same thing for 82. So we take 8 squared and 2 squared. We add those together. That's 64 plus 4, which is 68. Then we do it for 6 and 8. Square each of them. That gives us 64 plus 36, which is 100, I think. And then finally we do it for 100. Which gives us 1. And that's where we stop. Because 0 squared is 0. So this would just be 1. And because we hit 1, it ends in 1, so it's happy. So we return true. 19 is a happy number. I love how upbeat this problem is. So then let's do it again for n equals 2, because this should return false. And I guess it's never going to equal 1, but I want to see if it loops back on itself, meaning do we repeat any numbers? And if so, that's probably how we can tell that it's not going to be happy. So for n equals 2, that would be 2 squared, which is 4, 4 squared, which is 16. So then that's 1 squared plus 6 squared, which is 37. 3 squared plus 7 squared is 9 plus 49, so 58. Then we do 5 squared plus 8 squared, which is 64 plus 25, which is 89, I believe. 8 squared plus 9 squared. So that's, let's see, 81 plus, 64 plus 81, so that's 145. Now we get 1 squared plus 4 squared plus 5 squared equals, so that's 17 plus 25, which is 42. We've still not repeated anything. Hopefully this doesn't take forever. So that would be 16 plus 4, which is 20, which is 2 squared plus 0 squared, which equals 4. Okay, we repeated. Do you see that? If I zoom out a little. We got 4 here, and we've already had 4. And we know that 4 is just going to eventually loop back to 4. So this chain ends, and we never hit 1, so we return false. So that's what we have to do here. Now the only tricky part of this, so basically we're going to have a set. We'll have a set to track cycles, meaning we'll use a set to tell if we've ever seen the same number a second time. So we'll add every number we get, and if we ever see it again, we know we can return false. So we'll have a set to do that. And then for doing the actual taking a number, splitting it into digits, and adding the squares, the sum of squares of the digits, we can use a trick that some of you might have seen in Python before where we can loop over a number by taking off the ones digit and then dividing the number by 10. So let me show you what I mean. So say we wanted to get 19 and we wanted to turn it into this. We could loop over it, so there'd be a for loop. And each time we go through the loop, we would say sum, because we're trying to get a sum, equals sum plus, and then we would take 19, so I'll say it's called n. We take n modular division 10, because if we divide any number, if we modularly divide any number by 10, we get the ones digit. So that would equal 9. And then we raise that to the power of 2. So we square that. And then once we've gotten the ones digit, we need to cut the ones digit off. So we're left with just 1, and we can do that by saying n equals n divided by 10. So it's this cool trick where first you do modular division and then normal division. And this grabs whatever the ones digit is, and then dividing it by 10 cuts off the ones digit because it's integer division where you don't do floats. So yeah, hopefully that makes sense. And I think we can jump right into the code. I think those are the only two main things we need to talk about. So for writing this, I'm going to do exactly what I described. I'll start out by making a set. So we'll call it scene to track the numbers that we have seen. We'll just make that an empty set. And then I guess we can just loop while true, because we don't actually know how long this is going to run. On each loop, we're going to have a sum. And that'll start by being equal to 0. And then the first thing to do is what I just talked about on the whiteboard, which is we need to do the sum of squares. So we need to get the ones digit, square that, add it to the sum, divide by 10, and keep going. So we will say while, I guess. So while n does not equal 0, we will do, because eventually when we do this, once we process the last digit and we divide that by 10, it's just going to equal 0, and then we don't need to loop anymore. So while n is not 0, we can say sum equals sum plus, and then we can say pow, I think this will raise something to the power of something else. It might be math.pow, but I'll figure that out at the end. So we would say n modular division 10 and raise this to the power of 2. So what this line is doing is it's taking the ones digit of n, grabbing it with n modular division 10, and then squaring that, adding it to the sum. After we do that, we need to say n equals n integer division 10. So this cuts off the ones digit. So on the next iteration of the loop, we have the next number. So with 19, the first pass would consider the 9, then it would cut the 9 off. The second pass would consider the 1, then it would cut that off. We'd be left with 0, and then we would stop. So I think we can just do that. Then we would say, now we just check, okay, we calculated the sum. Is this sum equal to 1? If it is, it's a happy number. So if sum equals 1, we would return true that this is indeed a happy number. One other option is that sum is in scene. So if the number we've found before, we can return false because we know we're going to just keep looping and it's never going to equal 1, like the example we saw in the whiteboard. So in that case, we can return false. Let's see. There's one other case. Well, if neither of these happen, I guess I can just make these both ifs. If neither of those happen, What we want to do is add sum to the scene set. So we can say scene.add sum, right? Because in this case, sum is not 1, and we've never seen this particular sum before. So we need to add it to our set so we can check if we're cycling ever. We add it to our set, and then we need to update n. So n must equal sum now, right? Because like we saw in these examples over here, once I calculate the first sum, say it's 82, we need to then, on the next iteration, process 82 so we can cut it up. So in order to do that, I need to set n equal to sum so that we push forward whatever we've calculated, this loop to the next loop. I think that's it. Let's go ahead and run it and see if we found a working solution. Yes, that's working for the 2 test cases, but let's try it on everything. Yeah, fantastic. So that works. Runtime's pretty good, but again, we don't really look at that because it depends on the platform. Yeah, that's a really fun problem. I enjoyed that, and I think these math ones are going to get really interesting, especially as they get more difficult. But again, the main parts of this one to take away are this method for iterating over all the digits in a number. I think that's super useful and something that comes up all the time. And then yeah, I just had a set here to check for cycles. A set is a really good way to check for something that's repeating in a problem. So thanks so much, and I'll see everybody in the next video.